Is it visible?
Yeah. So, yeah, sure. So Divyesh is currently with TCS Research and is currently pursuing his PhD from IIT Bombay. And today he's going to talk about this exploiting induction and difference computation to verify array programs. Over to you, Divyesh.
Thank you, Sean, for the kind introduction. So today I'm going to talk about how to verify programs while exploiting the synergies between induction and what I call difference invariance. So just to motivate, arrays are extensively used in embedded and safety critical applications. And these arrays, they are of parametric size. So this is done to ensure that the same software can be deployed on various different models or appliances. And before such software is deployed on an appliance, the size is instantiated in accordance with the model where it is being deployed. There are various libraries that also manipulate arrays of parametric sizes, and these libraries are used in various different applications. So verifying parametric properties of such software before they are deployed on an appliance, it's really important for safety. And it turns out that it's really challenging. As an example, consider the function foo that updates an array A, which is of parametric size n. The array may be updated in nested loops and branch conditions and so on. The program parameter n may be used in loop bounds, conditional expressions, as well as expressions in assignment statements. I'll refer to such programs as Pn, that is a program with parameter n. I'll denote the preconditions as phi n and the post condition as psi n. These are also parametric in n. They can be quantified or quantifier free, and they may have potentially nonlinear terms. So the goal here is to verify that this parametric Hoare triple phi n, p n, psi n, it holds or not for all values of n greater than 0. So you want to essentially establish that this Hoare triple holds. For the ease of explanation and for simplicity, I have taken a Hoare triple with a single parameter n. The technique is general and it works for multiple parameters as well. So there are various tools and techniques that have been developed to verify properties of programs with arrays. These tools and techniques, they rely on various approaches from abstractions to computing loop invariants and so on. So one particular technique is of interest to us, which is the full program induction technique that was published at TACAS 2020 last year. And we're going to build on this technique and we'll show that our work is significantly better than this full program induction technique. So we'll look at full program induction in detail. So essentially the idea is that we induct on the given program Pn via the program parameter n instead of inducting on the individual loops. And just like any other inductive technique, we check the base case wherein we verify that this Hoare triple holds for small values of n, say n is equal to 1. If the base case fails, then we have found a true counterexample. In the induction hypothesis, we assume that the Hoare triple with parameter n minus 1 holds. Now, in order to verify the induction goal using the induction hypothesis, what full program induction does is it computes a code fragment delta Pn called the difference program such that the sequential composition of program with parameter n minus 1, which is Pn minus 1, and the difference program is semantically equivalent to the given program Pn. It also represents the precondition phi n as the composition of phi n minus 1 and delta phi n. Delta phi n is called the difference precondition. Whenever the program Pn minus 1 does not modify the variables in the difference precondition, it is directly available as a precondition to the difference program. Now notice that in the inductive step, the proof of the Hoare triple on Pn minus 1 is available for free from the induction hypothesis. So essentially, in the inductive step, I just need to verify the Hoare triple on the difference program. And now this is easy because in many cases, the difference program may be loop free, and I can feed it directly to a model checker to verify this. Notice that the entire reasoning is on the entire program itself and not on individual loops. In many cases, it may turn out that the inductive step may not be immediately verifiable. In such cases, what full program induction does is it will try to strengthen its precondition. So it tries to infer a formula pre n minus 1 to strengthen the precondition of the difference program. And since we are in the inductive reasoning, any formula that holds after n minus 1th step must also hold after the nth step. So pre n simultaneously strengthens the post condition as well. So this iterative process continues until either the post condition is verified or the technique is no longer able to infer new preconditions to strengthen the precondition and post condition of the difference program. Dijkstra's weakest precondition computation can be used to infer such preconditions. Okay. So there are several advantages of using such an inductive technique. First of all, it simplifies the verification task, especially when the difference program is loop free. Secondly, computing several quantities is easy. For example, computing Pn minus 1 and Psi minus 1 just requires substituting n with n minus 1. The post condition of the induction hypothesis is directly useful during the inductive step, as we have just seen. And computing the difference program for several classes of programs is fairly simple. And to illustrate, I'll just share a couple of points to give you an idea of what are the kind of classes for which computing the difference program is easy. So if there are no data dependencies amongst the variables that are modified in loops as well as across loop iterations, and there are no data dependencies on the program parameter n, in such cases, the difference program is very simple. The difference program can be computed for other cases as well. However, there are several difficulties en route, and in the rest of the presentation, I'll focus on these difficulties and how we go about solving these difficulties. So consider this program which has sequentially composed set of loops, and here the program parameter n is used in loop bounds as well as in assignment expressions. The first loop modifies a variable x whose value is dependent on its value computed in the previous iteration. The second loop modifies the variable b, array variable b, and its value is dependent on the variable x, which is modified in the first loop. So there are various dependencies across loop iterations as well as across loops. And the values of these scalars as well as arrays are dependent on the program parameter n as well. So if we try to apply the full program induction technique, it will have to compute these programs Pn minus 1 as well as the difference program. So in Pn minus 1, all the occurrences of n are replaced with n minus 1 as shown here. So this results in values of variables being different from their values in the program Pn. For example, x is computed using the expression n minus 1 squared in Pn minus 1, whereas it is computed using n squared in Pn. And what the difference program will essentially try to do is, it will try to repair the values of such variables as well as scalars. So here there are these loops that are trying to repair values of variables and scalars. And the difference program will also try to account for the loop iterations that are missed in Pn minus 1, which are present in Pn. So these loop iterations are shown by colored boxes with solid lines here. Now we can already see that this difference program is fairly complicated, and constructing such a difference program is non-trivial in general. Also note that the difference program here has two loops which are sequentially composed, and because it already has loops, the verification task may not be any simpler than verifying the given program Pn. So analyzing delta Pn may be as hard as analyzing the original program P. So in such cases, what full program induction would try to do is it will try to reapply the same technique again to see if it can further simplify the difference program. And apparently it has to do this even for programs with non-nested loops. So now let us try to see how we try to overcome these difficulties. So before we do that, There are several other difficulties that it will face apart from the difficulties that I just described. So whenever the program has branch conditions that are dependent on n, computing the difference program is a challenge, because when n gets substituted with n minus 1, the program Pn and Pn minus 1 may take different branches. And this poses difficulties in terms of rectifying the values of variables that are computed in the loop. So computing the difference program itself gets very challenging. Further, when the program has nested loops, then again computing the difference program is very challenging. It has to account for the differential number of loop iterations, as well as it has to rectify values of variables that are modified inside the nesting. So this idea of inducting over the entire program is very interesting. And it has, as I already shown, it has several advantages because it allows us easy access to the induction hypothesis. However, the main challenge is in computing the difference program over there. So we try to ask if we can reduce that difficulty of computing the difference program. And in general, verification is tough. If you try to reduce the difficulty in one task, it's likely that you will end up paying in some other task. So clearly there is a trade-off here. And the trade-off is in terms of the ease of generating the difference program versus the ease of using the induction hypothesis. Remember, during the inductive step, the proof of the whole triple on Pn minus 1 was available for free from the induction hypothesis. So if we try to simplify difference generation, that may not be the case. And in our work, we have shown that this ease of generating the difference program is more beneficial. That is, you can let go of this ease of using the induction hypothesis. And I'll show you why this is the case in a couple of slides. So this is the whole triple from the induction, a full program induction thing. And essentially, as we have already said, computing the difference program delta Pn is difficult. So we do not want to compute such a difference program which is complicated. We want to use a simpler program over there. So what I'll do is I'll instead use peel Pn. And by peel Pn, what I mean is just the peeled iterations of all the loops in my program Pn. And now instead of Pn minus 1, I'll use a slightly modified program Qn minus 1. So here the modifications are that n is substituted with n minus 1 only in the loop bounds and not in the conditional expressions or in assignments, unlike in Pn minus 1, where n is substituted with n minus 1 across the entire program. Now, since Pn minus 1 is different from Qn minus 1, the post condition is also different. That is, post condition of Qn minus 1 is psi prime n minus 1. And instead of using the whole triple on the left, now I want to start using the whole triple on the right. Okay. And in our work, there is also some difference in terms of the way we decompose the given precondition phi n. I'll just show you in a couple of slides how we do that. But essentially, Qn minus 1 differs only from Pn in terms of the loop bounds. Otherwise, they are very close. And so in order to compute psi prime n minus 1, I'm going to use psi n minus 1 and the differences between the program Pn minus 1 and Qn minus 1. And these differences are nothing but difference invariants. And as I said, peel Pn is just the peel iterations of the loops. And now essentially there is some cost that I'm going to incur, and that cost is in terms of ensuring this implication. So what this implication says is, whenever the induction hypothesis holds, that is the whole triple on program with parameter n minus 1 holds, then I must ensure that the whole triple on program Qn minus 1 also holds. And for me, this whole triple on the right is available by construction. I'll just show you how. So let's take a program. So this is the program that we have already seen, which has two sequentially composed loops. And for this program, applying the full program induction strategy is difficult because constructing the difference program is quite challenging. It is fairly complicated. And as I just told you, I want to use peel Pn as my difference program. Peel Pn, as you can see here, is just the peels of all the loops in the program. And in Qn minus 1, only places where n is substituted for n minus 1 is in the loop bounds. Otherwise, it is very close to the program Pn. And the way I compute Qn minus 1 is as shown here. what I do is I take my given program and I peel each loop in the program. That is, I peel the last iteration of these loops. Then I identify the uses of variables that are modified in the peel. So for example, here, X is being used in the second loop that was modified in my peeled iteration. And such uses I substitute with the expressions that are assigned to them in the peeled iteration. So that is shown over here. And now the peeled iterations are independent of the code that follows such peeled iterations. So now I can move this peel across the second loop, and that results in this sequential composition. So it turns out that this process can be algorithmized, and there are several guarantees that I can give here. So the main guarantee being that the sequential composition of Qn-1 and peel Pn is semantically equivalent to the given program Pn. We can also do this for a restricted class of nested loops. So consider this nested loop where the loop counter of the outer loop goes from 0 to n, 0 to n minus 1, and the loop counter of the inner loop goes from 0 to I. And the way I go about doing this here is I view this loop as where the inner loop is fully unrolled. So since the inner loop executes I times, I have shown the unrolling here that there are I iterations inside the outer loop. And now I can peel this, I can easily peel this loop. When I peel this loop, n-1 iterations of the inner loop, they become part of my peel here. And hence my peel has a single loop where j goes from 0 to n-1. Let's take another example here. So in this example, j goes from 0 to n. And when I unroll the inner loop, there are n iterations of the inner loop that become part of the outer loop. So when I peel this, when I peel this, the last iteration of the outer loop is shown over here. Then the n iterations of the inner loop become a part. But not only that, the last iteration of the inner loop, which was missed for the initial iterations of the outer loop, also become a part of the peel. And so in my peel, there is a set of sequentially composed loops, which are as shown here. Okay, and I have shown indices just to show you how the variables are getting modified in the iteration space. So it turns out that for a restricted class of nested loops, this is fully automatable. And there are several guarantees that again we can give. So I'll just talk about what are the restrictions that we impose here. So I have shown the grammar that we use. It is fairly general. The only restrictions that I'm going to impose are, I'm not going to allow unstructured jumps, and I'm not going to allow updates to the loop counter within the loop body. So apart from that, we are going to assume that the upper bound expressions of the loops, they are in terms of the program parameter n, and in terms of the loop counters of the outer variables, outer loops that cover this loop. And for the ease of presentation, I'm saying that the nested loop, if at all the nested loops are present in the program, then they are the last loops in the sequence. The technique is fairly general than that. And I would request you to refer to our paper for how we have generalized this restriction. So here are the guarantees that we give. So whenever the program satisfies these syntactic restrictions that we just stated, and when the upper bound expressions, they are linear expressions in n and the loop counters, then we guarantee that the maximum nesting depth in the peel Pn program is strictly less than the loop nesting depth in the given program Pn. That is, each application of our technique will reduce the verification complexity. And the other guarantee that we give is that the sequential composition of Qn-1 and peel Pn is semantically equivalent to Pn, that is, it preserves soundness. Okay, so that was it about computing Qn-1 and peel Pn. I'll explain how we decompose the given precondition using an example. So consider that my precondition is as shown here, that is for all I in some range, a of I is equal to n. It turns out that there is no difference precondition that satisfies this implication, which is required by the full program induction technique. So what this implication essentially is saying that if a of I is n, that means that if a of I must also be equal to n minus 1. And certainly that cannot happen. So the way we go about doing this is that instead of substituting n for n minus 1 throughout in the entire formula, we substitute it only in the ranges. And that gives us two formulas, phi prime n minus 1 and delta phi prime n. And it can be seen that composition of these two formulas is essentially implied by the given precondition here. Now, whenever this difference precondition as computed by our technique is such that qn minus 1 does not modify variables or arrays in this formula, it is directly available as a precondition to peel Pn. For computing the post condition of qn minus 1, that is psi prime n, what we do essentially is we infer relations between the variables in the program qn minus 1 and the program pn minus 1. Now, this is very similar to what happens in translation validation techniques, where they try to infer relations between two slightly different versions of a program after a transformation has been applied. We call such relations as difference invariants. So these difference invariants are going to relate corresponding variables in program Q and program Pn minus 1. Okay, so once this difference invariants are computed, I can compute psi prime n minus 1 using psi n minus 1 and this difference invariant. And it turns out that whenever these difference invariants are just equalities, I can compute psi prime n minus 1 just by substitution. If there are inequalities, I may need a quantifier elimination. From our experiments, we have seen that computing the difference program is fairly simple. Especially it's simpler than computing loop invariants for each loop. And we use a guess and check approach with simple templates that are shown here. The functions are essentially parametric in terms of I, n, and other program variables, and they are linear or at most quadratic. So let me take an example so that I can show you what kind of difference invariants I compute and how they look like. So here is a whole triple. There is a precondition which says for all I in the given range, a of I is equal to n. And there is a program Pn with a sequentially composed set of loops. The first loop aggregates the content of A in variable x. And the second loop computes each element of array B depending on the value of x and the loop counter j. And there is a post condition psi n, which is again a quantified post condition. And it says B of I is I plus n squared. So if we try to verify this post condition directly using loop invariants, this is the kind of loop invariants that you will need. For the first loop, you will need x is equal to I into n at the loop head. And for the second loop, we'll need for all k1 in some range, that is 0 to j, b of k1 is k1 plus n squared. So notice that computing these loop invariants is quite difficult. They are quantified loop invariants over arrays and possibly non-linear terms. And so here I have just shown program Pn minus 1, where n is substituted with n minus 1. And that substitution also carries two loop invariants. Now I'll show you how our technique goes about doing this. So we'll compute this program Qn minus 1, as I have already described. So notice that the bounds of loops here is n minus 1 instead of n. Otherwise, it's the same as Pn. And we want to essentially compute psi prime n minus 1. So we'll start by computing the differences of variables that we have seen in the precondition. So here is what my difference invariants are going to look like. For preconditions, it says for all I, the difference in a prime I and ai, that is variables and arrays in Q versus the variables and arrays in Pn minus 1, is given by this relation. A prime I minus ai is 1. And x prime minus x is n minus 1, because in each iteration, there is a difference of 1 that gets accumulated. And similarly, for the second loop, it's for all j, b prime j minus bj is 2n minus 1. So notice that whereas loop invariants were non-linear, here my difference invariants are no longer non-linear. And they only relate corresponding variables between the two program versions. So it's really easy to put a template on these kind of invariants. Now, once we have computed these difference invariants, we can compute the post condition using the formula that I had just shown. And it turns out that the post condition is as shown here. Psi prime n minus 1 is for all I in the given range. b prime I is I plus n squared. So once this post condition is computed, now we can go for the inductive step. Again, I would like to draw your attention on the fact that the entire reasoning is on the given program itself as a whole program and not on the individual loops. Our technique can verify post conditions which are existentially quantified or they have quantifier alternations. So there is a restricted set that can be done. So here I have shown a simple program that computes maximum, and the post condition says that essentially there is an index in the array A where you can see the value of this maximum that was computed by the given program. And in order to verify this post condition, we again go by the same.
Divyesh, you have 2 minutes left.
I have 2 minutes?
Yes.
Okay, sure. So in the interest of time, I'll skip how we go about doing this, but it's fairly simple. We follow the steps that I have outlined. It may turn out that we may not be able to verify the inductive step immediately, in which case we again rely on computing weakest preconditions. So here I have inferred psi prime n minus 1 to strengthen the precondition. And since I'm using qn minus 1, this formula may not be used to strengthen the post condition as well directly. But it turns out that these are related through the difference invariants, and computing them is fairly simple, especially when the difference invariants are equalities. So here is the soundness guarantee that my technique gives. So if the base case holds for the strengthened post condition, and that any inferred formulas for strengthenings, they are related through the difference invariant, and that the inductive step holds for the strengthened pre and post condition, then I guarantee that the post condition holds for all values of n. Based on these ideas, we have developed a prototype tool called Diffie, and we have experimented on a large class of programs, more than 300 programs from the software verification competition as well as from other sources. We have compared against various tools such as Vajra, Variabs, VIAP. These are state-of-the-art tools in terms of proving programs with arrays, and they have won the software verification competition several times in the past. The timeout was set to 60 seconds. So here is a snapshot of this that we have obtained. So this is the summary. And as it can be seen from the summary, our tool Diffie is able to verify most of the programs that are part of the test suite, whereas other tools struggled on several of them. We have divided the test suite in 3 different categories. The first category, there are simple programs which compute min, max, copy. These are really easy for tools such as Vajra, Variabs, VIP. In the other categories, C2 and C3, there are programs that are slightly difficult, where computing the differences are really hard, or they have nested loops. And it turns out that our tool does really well on the class of programs that I have just shown here. So in terms of time, also we do much better as compared to other tools. We are 10 times faster than VIP and Variabs on most programs. So the cactus plot on the left is on the safe programs in the benchmarks, and the plot on the right is on the unsafe benchmarks. To verify the unsafe benchmarks, we report unsafety only when the base case check fails. Its performance was comparable to Vajra on C1 category, and it did outperform Variabs and VIP. However, in C2 category, where there are nested loops, Vajra and VIP really struggle because they do not support such programs. And Variabs, however, Variabs was able to verify a few programs in C2, C3 category that my tool was not able to. This is cases where I'm unable to compute the difference invariants, or I'm unable to strengthen the pre and post conditions. So here are some of the takeaways. This paper was published in CAF 2021 that describes this technique. The artifact was accepted as functional and reusable. It is available at the link shown here. You can scan the QR if you want to go to that link. To conclude, I presented a novel inductive reasoning technique, and the technique exploits the synergies between induction and difference computation. By difference computation, I mean computing the difference invariants that relate variables in 2 versions of the program. Computing the difference invariants are often simpler as compared to computing loop invariants. In the future, we would like to survey the literature in translation validation and exploit several techniques that they use for computing differences, so that we can expand the scope of the programs that we can verify right now. That is all from my side. I'll be happy to take on questions. I'd like to thank
you, Divyesh,
for giving me this opportunity. Thanks.
And, yeah, open to questions. So any questions from the participants? Okay, so I have just one question.
Sure.
How difficult it is to compute Qn minus 1 when there are complex computations happening in between the loops? That is, let's say after L1 and L2 in between the loops, there are some other computations happening which make use of the variables modified in the previous loops.
It's fairly simple. I mean, all you need to do is wherever you are using any variable that is modified in the peel of a loop that was before that statement in between loops, that has to be substituted with the expression that is assigned to it in the peel, and then the peel becomes independent of the code that follows it. It's as simple as that.
Okay. So if there are no more questions, let's thank the speaker.
Thank you.
Yeah.